Hello, everyone. Welcome to GROOT. Today we'll be hearing from Khyathi Komalan on non-Hermitian ribbon fusion categories.
Hi, so I'm Khyathi Komalan. I'm a licensed sophomore at Caltech. Today I'll be talking about non-Hermitian ribbon fusion categories. Thank you so much for giving me the opportunity to speak today. I had to reschedule this a couple times due to like a few personal emergencies, but I'm glad that I finally get to talk. So yeah, I'll get into it. So the way this is going to work is I'm going to be motivating this using a little bit of math and physics because I feel like this is a topic that is relevant to both like representation theory from the math side and is also like rather relevant to like quantum mechanics and stuff. So yeah, I'll be starting with the motivation today. So yeah, one of the prime motivations for studying fusion categories in general is representation theory. So the way you can think about representation theory is sort of like de-abstracting algebraic objects in a sense. So algebraic objects are like obviously like pretty abstract, and it's kind of hard to say, like if you're not a mathematician or even if you're a mathematician sometimes for like more complicated structures, like what exactly it entails and like what kind of data it represents. So I guess the point is like the abstracting abstract objects to matrices or like something more computational that's like more easy to work with. So in the context of fusion categories in particular, which I'm going to be motivating, we'll be caring about the representation theory of groups. That is basically seeing how groups can be like de-abstracted and like represented, based on like vector spaces and matrices and stuff. So yeah, uh, the representation of a group G on a vector space over the field K is basically a group homomorphism from G to the general linear space of a vector. So this is basically like all the invertible linear transformations in the vector space. So the goal, basically, when you define a representation in such a way, is that each element in the group would correspond to like invertible matrices. Um, and the group operation would be matrix multiplication. So now the data is like in terms of matrices, and you have something that's like more computational to work with. So it's not as abstract as it was before, and therefore becomes a little bit more concrete. So one example is that in math, we often capture like a lot of abstract symmetry using Lie groups, and you can compute the representations of the Lie groups, and that gives you a more like concrete notion of symmetry. And then the motivation from the other side of physics is mostly related to quantum mechanics. So we can clearly see from the previous sides that representation theory is about this kind of de-abstraction, and also sort of about this notion of symmetry that it's basically helping you try to understand. And the notion of symmetry is also rather relevant in physics and especially in quantum mechanics. So the point of quantum mechanics is sort of to like understand like how things kind of work in the particle scale like of an atom, and like how these things interact with each other, which is sort of unpredictable. So you have like a lot of like complex systems, complex equations, and a lot of stuff like defining each other. So it would be nice to be able to like assign an algebraic object and then de-abstract it to get a sense of like the symmetry of these particles. So yeah, you can use Lie groups to do this for classical systems to get like a symmetry or like a representation of symmetries. And then similarly, if you're working in like a more quantum environment, you would be using quantum groups. And yeah, so quantum groups basically represent the symmetries between particles in quantum mechanics. So here you can kind of see like a vague link between representation theory and physics. So the next obvious move would obviously be trying to somehow study the representation theory of quantum groups. So let's think about a problem. So if we have like two particles and these two particles have different symmetries, and these symmetries would obviously would be able to be represented in terms of quantum groups. And let's say we have another particle that's like a combination of these symmetries. And like what would be the corresponding algebra is a good question to ask. So say you have two particles like P1 and P2 and two distinct symmetries that's representing it like S1 and S2. Perhaps the suppose you have like particle P3 And the symmetry is like a combination of the symmetries of particle P1 and particle P2. And that would be a combination of the symmetries S1 and S2. Like, so you would be tensoring the symmetries S1 and S2. So kind of the obvious way of combining these symmetries would be using tensor products. And then there's more examples of symmetry that you can think of in math that makes things even more simpler. Perhaps like the most simplest example of symmetry in math would be commutativity in a sense. And that's like the property where A times B is equal to B times A. Like we see it everywhere around us, like say like multiplication in like the integers and like stuff like that. So yeah. So now we have this idea of representation theory as the abstraction and tensor products as this idea of us like being able to combine these things in a sense. And yeah, so now it's kind of a good thing to start thinking about like what would be like the more nicer and well-behaved portion of this tensor product, and that might be the part where it's like commutative or like more symmetric in a sense. So what we are trying to do now is basically combine all of these notions together. So yeah, that's what we'll be tackling now. So now that we have like motivated all of these different kind of stuff, um, we'll get to the definition of fusion categories. So what fusion categories basically do, essentially, is that we'll be combining these ideas of representation theory, breaking things down, and also of tensor products, combining things. So what you want to be working with is basically a structure where you're able to combine simpler things to make something more complicated, and also be able to break down these complicated structures into something more simple. So category theory is basically all about being able to combine all of these different ideas together in a sense, because it's so abstract. So that's why working in a categorical setting definitely makes sense. Yeah. So currently we have the representation theory and tensor products that are useful like to encoding the intersection of representation theory and quantum mechanics. But like as we discussed, we know that commutativity is this it's kind of a really nice kind of symmetry, right? So that would be a greater portion to like discuss. So the way commutativity is represented in category theory is basically the portion where like we want to be studying the portion where the tensor product is commutative. And that would be done through braiding. So when you define a braid on a category, you have a few properties that come with it and a few equations you should satisfy. But that's not really sufficient for us, and we want to be working in like maximums and lambda and like to capture like more of these ideas in a sense. So I thought it would be nice to add some extra structure, and you define something else known as a twist. And a twist is kind of a natural isomorphism that's like between like these objects that like satisfy like certain conditions, kind of. So you can also that like the addition of a twist on a braided fusion category basically makes it a ribbon fusion category. And you can mention the quantum dimension of objects in ribbon categories as scalars, and these scalars give you information about the size of the object related to the category and like how the structure behaves and things like that. And the twist and how it's defined also gives you information about these invariants and how they behave with each other. So that's the entire point of a twist. It basically gives you more information about how these invariants behave with each other and how like in a sense like how these different braidings relate to each other. So a category with a braiding and a compatible twist is basically a ribbon category. So now combining all of these together, we basically get ribbon fusion categories. So a fusion category is basically a category that is abelian, k-linear, semi-simple, monoidal, rigid, and has finitely many classes of simple objects, and whose monoidal unit is simple. So what this basically means, like all of this jargon apart, is that so it basically means that you have this idea of like being able to take objects and break them down into simple objects, and then you have a tensor product defined on this category. And rigidity essentially means that like you're kind of able to do this breaking down thing in the first place. Like if you were able to take something more complicated and then break it down into like simple objects, you have this kind of relation between like the co-evaluation and evaluation morphisms. And yeah, and this category is kind of enriched into the category of K modules. So yeah, that's basically the idea that's being shown around here. And a ribbon fusion category, as discussed before, would basically be a fusion category that has both a braiding and a twist equipped with it. A braided fusion category is a fusion category equipped with a natural isomorphism or a braiding, satisfying certain properties known as the hexagon axioms, which are written here on the screen. So continuing that, you also have another natural isomorphism that's a part of this category called the twist. So the twist is basically a natural isomorphism like to the object itself, and it satisfies like two conditions. So twist should be compatible with the braiding in this sense, and it also should be compatible with duality. And the reason I used ribbon fusion categories, it was kind of inspired by these notes on topological quantum computation that I found that use ribbon fusion categories a lot. So now we'll understand the connections with physics like further and why we even care about ribbon fusion categories or fusion categories in general from the physics point of view. So my main inspiration is a paper titled Categorical Quantum Mechanics by Samson and Abramsky, like Samson, Abramsky, and Bob Koike. Um, and in this paper, they basically model a lot of math in quantum mechanics, which lives in Hilbert spaces using Dagger symmetric monoidal categories and Dagger compact categories. And this basically models a lot of math in quantum mechanics. So a Dagger structure on a category C is an involutive contravariant endofunctor. So this means that the dagger goes from the category C to itself, and it assigns each object A in C to another object, and like each morphism to another morphism F dagger, which goes from B dagger to A dagger in C, and it has certain properties holding. So it's like as defined earlier, it's involutive, contravariant, and endofunctor, and these each mean different things. So when you say that the dagger is involutive, you basically mean that F dagger of dagger is equal to F for all morphisms of F. And if you compose G and F and take the dagger of it, it would be equal to F dagger compose G dagger. And dagger is an endofunctor. So that means for each object A in the category, A dagger would be equal to A. So if a category C is equipped with such a functor, you call it a dagger category. So now the thing is, there's two different kinds of dagger structures. One is called Hermitian or unitary, and the other is called non-Hermitian or non-unitary. So currently, I think there's a lot of properties being deduced and a lot of results being done on Hermitian dagger categories and like how they behave. And this is because they're like a lot easier to work with, and the calculations are like kind of more elegant in a sense because you have like more symmetry and more properties to work with. Whereas the non-Hermitian case is a little bit messy because it's kind of limited what you can use and what you can't use. So going to definitions, in a Hermitian dagger structure, we have F compose F dagger if and only if F equals 0. And in a non-Hermitian dagger structure, this is not necessarily true. So like I said before, in the case of quantum mechanics, a lot of the math lives in a special vector space known as Hilbert spaces, which carries its own different set of properties. And in the paper I mentioned before, the category of Hilbert spaces has a Hermitian dagger structure. And for other like physical structures, like this is a little bit more complicated. Like you don't necessarily need to have a dagger structure that's Hermitian in nature. So you need to also consider the cases where the other kinds of categories where you do have a non-Hermitian dagger. And in areas like condensed matter physics, you basically want to consider open systems, and they have like much more interesting topological frameworks. And in these frameworks, you don't necessarily have this kind of idealistic kind of symmetry even within the math, and therefore you can't really be using this Hermitian structure. And in fact, it was comparatively more recent that they found out that fusion categories could even have a non-Hermitian structure. And the first counter example that was found was the Yang-Lee category. And the Yang-Lee category is an example of a non-Hermitian fusion category. So that does prove existence on that side. So now it's important to understand why exactly having a non-Hermitian dagger structure is annoying and why it would be more ideal to have like a Hermitian dagger structure and what kind of problems these present so we know exactly how to circumvent it and work around it. So in Hermitian categories, the dagger operation behaves nicely with conjugation and involution properties. And what this basically means is that the equations like behave a lot nicer because you're gonna be taking adjoins a lot and these satisfy like certain properties that's like compatible with like the whole structure of the category, making it like much easier to work with. And you have a lot more equations that you can use, which really helps with the algebraic manipulation. Whereas in non-Hermitian structures, you don't have this compatibility and like you don't have these properties to rely on. So you're basically left with using the rest of the properties of the like the categorical structure, which is a little bit hard to use and might be also resulting in like more general results rather than something more specific that we want. So within permission categories, these unitary properties that we have, um, ensure that like the braiding and twist operations preserve like certain properties when it comes to like orthogonality and non-conservation and stuff. And without these unitary properties and non-Hermitian structures, it's kind of hard to ensure the consistency and coherence in braidings and twist operations. And this means that you'll have to make a lot of constructions using the data that you do have in order to understand exactly what these things mean. So in her mission categories, the evaluation and co-evaluation morphisms have more symmetry and duality properties, and this basically simplifies the categorical framework in a sense on how you can work with it categorically. And however, in non-Hermitian categories, this is basically useless, and you don't have these straightforward properties, and you'll need like more complex definitions and verifications to achieve like the same things that you want. For example, in the construction that I'm going to discuss today, um, if it were a Hermitian category, we could basically define things using the properties that you would expect the evaluation co-evaluation maps to have. But because we're working with a non-Hermitian category, you kind of have to do some picking and choosing when it comes to like what morphisms you're working with, and you have to like define them in terms of other stuff. And the stuff's a little bit tricky to see in comparison to how it would be in a Hermitian structure. So in Hermitian categories, the dagger operation behaves nicely with complex operations like conjugation and the involution properties, and this makes manipulation of symbols much more easier. And in non-Hermitian structures, you basically cannot rely on any of these things. So a partial resolution to this problem would be to investigate the Müger center of the category, and this is the full subcategory generated by V, defined as follows, where the braiding satisfies a certain property. And in this particular Müger center of the category, it's like much easier to be able to work with these things. And you can kind of lift the results that you get in the Müger center up and like lift it up to like the entire category in a sense. And yeah, so that's definitely one workaround. The other workaround would be using the other properties that we have. For example, here we're discussing non-Hermitian ribbon fusion categories. So you would be using the ribbon structure, the definition of a fusion category, and things like that. So moreover, in Hermitian categories, unitary properties basically ensure that braiding and twist operations preserve certain orthogonality and norm conditions. And yeah, so like this was discussed earlier, uh, so you basically want consistent coherence in like the braiding and twist operations that we do not have. So we'll be defining new kinds of braiding operations. Um, and we'll have to like kind of redefine the hexagon axioms from scratch and making sure like what's compatible with the rest of the structure that we have without assuming too much. And basically we want to be able to define a braiding that we can actually work with and whose properties that we can actually use. And when it comes to the issue of evaluation and co-evaluation maps, we'll basically be making use of the zigzag identities, which we can rely on because we do have at the end of the day a braiding and a twist. And obviously the category is also monoidal. So these things help a lot. So yeah. So now I'll be talking about a TQFT construction that an idea for it that you could make using all of the things that we have discussed so far. So in order to construct a TQFT from the non-Hermitian Dagger structure, well, it's certainly not straightforward. People know how to do this from the Bin fusion categories. People know how to do this with Hermitian fusion categories, but the non-Hermitian case has been rather tricky, because of like all of the problems that I've mentioned now. And the reason why I personally would be interested in a non-Hermitian case is because I would hope that in a field like condensed matter, which is like a little bit more about asymmetry and stuff, something like this would be a little bit more valuable and useful. So now we would basically be taking inspiration from the ideas that we have and how to circumvent it. And so we'll be basically working on that. So like I discussed earlier, sorry, give me a second, the slides. We are basically going to be following the blueprint of the resolutions I found for the problems that we would be facing. So we would in the Müger channel of the category. So if C is an Hermitian Dagger structure, can you see my screen? I'm not sure what happened.
Seems to have disappeared.
I'm sorry.
The screen disappeared.
Oh, what? Sorry about that.
Yeah. I think it's just the connection. You started lacking and then the screen disappeared. There we go.
Visible now?
Yep.
Yeah. So
So there seems to be a problem with the connection. Maybe you can try and take the camera off. See if that helps.
hello.
Hello. It seems like you have a problem with the connection, and your screen disappeared again. Maybe you could try and turn off the camera just to see if that helps, and then share your screen again.
Yeah, sorry about that.
All right.
Is it visible now?
Yes.
Yeah. So for the implies part, we would be assuming that C has a braiding, and you'd be using zigzag identities, evaluation and co-evaluation morphisms. And I'd mentioned earlier that if we were working in something that's like Hermitian, we would be able to use the properties of evaluation and co-evaluation morphisms and basically prove things using that. But I want to be avoiding using like all of the properties that come with it. So we'd be picking morphisms, like defining them based on the structures that we do have and working with them. And we would eventually be showing that the center is symmetric. And then we will show that the dimension of each simple object in the Müger center is 1. And then we would be proving the implied by part, and so you'd be assuming that the center is equivalent to the category of vector spaces, and you would define a braiding on it and lift it up to the transparent and non-transparent parts of the category. So this is basically would be considering the parts where the braiding is trivial and where the braiding is non-trivial separately, and So you'd be using, and you'd also be using the definitions of fusion category and like the other properties of braiding that come with it. And the second theorem, if C is a braided fusion category with a non-Hermitian dagger structure, then there exists a unique dagger compatible braiding on C, and we can define a Hermitian dagger structure on G to C. So the proof sketch for this is that we use that as a braiding on G2C from theorem 1 that we had proved earlier, and then use the decomposition properties of fusion categories to verify the existence of a dagger compatible braiding on simple objects alone, and we would be lifting this up to like the semi-simple objects. And if you assume that two such braidings exist on like these objects, and you will realize that the braidings are equal, and therefore you would be able to prove uniqueness. And the third theorem is basically where you'd be guessing that every non-Hermitian ribbon category admits a unique spherical structure that is a natural isomorphism V of x from x to x, x dagger dagger, satisfying certain coherence conditions. So now we use all the data that's like available in non-Hermitian ribbon fusion categories like the association, the right and left units, and define a suitable V of x, Vx in terms of these. And we'd be showing that Vx is a monoidal natural isomorphism. And then you'd be using that to verify the spherical condition. And this is basically a lot of commutative diagram chasing essentially. And you'd be basically using a lot of composition and stuff. And then you'd eventually realize that V is actually unique. So now the main result of this talk that I'd like to discuss is a possible TQFT construction. So the main result is that if C is a non-Hermitian ribbon category and it has a non-Hermitian dagger structure on it, then there exists a unique 3D TQFT defined by a functor from the category of ribbon tree bordisms to the category of vector spaces, where bordered lib tree is, as I said, the category of 3D ribbon bordisms, and vect is the category of vector spaces over a field K. So the way you sketch this is, first of all, you'd be using all of the theorems that we have so far to kind of prove the existence of such a structure. And then on objects, these objects would be 2D ribbon surfaces. So for a 2D ribbon surfaces given by sigma, we define G of C of sigma to be a vector space of natural transformations, which would be the homomorphisms from IDC to F sigma, where F sigma goes from C to C, and this is the ribbon graph functor associated to sigma. And the existence of the ribbon graph functor basically relies on all the theorems that we proved so far. That's theorem 1, 2, 3. And then on morphisms, you define it separately, and the morphisms are 3D ribbon bordisms. So for a 3D ribbon bordism M from sigma 1 to sigma 2, we would define GC of M that goes from GC of sigma 1 to GC of sigma 2. And this would be a linear map induced by the cylindrical functor CM from C to C that's like associated to M. The cylindrical functor Cm is well defined due to braiding, twisting, and like the spherical structure that we have defined on C. So this basically gives you a possible TQFT construction that arises from this non-Hermitian ribbon fusion category. So now I'll be discussing some scope for future work and what you would be able to do with these new categories and like the properties and like the theorems that we have proved like related to it, and also the TQFT construction that we have. So now that we have successfully established an idea for the construction of a TQFT, it would be advisable to proceed further thinking about fusion categories and perhaps investigating other properties related to fusion categories, such as evaluating the SMT matrices of these non-Hermitian ribbon fusion categories. So this would basically give you more data on like how these categories interact. Yeah. And then on the quantum side, you can basically compute the Hopf algebras of these categories, and you can like try to deduce the relationship between these Hopf algebras and the categories itself, and get an idea of the kind of information that they can give us about these categories. These directions are basically inspired by the directions that people took after there were results that were found on like Hermitian fusion categories. And finally, I think that TQFTs are like the foundation of condensed matter. So like they represent the lowest energy point, and it could be a good idea to think about how non-Hermitian within fusion categories can be used to model condensed matter and like how it could fall short or like how it could actually capture more symmetry in a more complicated sense than regular fusion categories are able to, or Libin fusion categories are able to, because the addition of a twist and the fact that like you don't have to necessarily assume that the dagger structure is Hermitian definitely gives you a lot of flexibility on what you're able to do with like minimal assumptions. So I think that's something pretty useful too. Next, I'll be going on to the references. So the references that I used in this presentation are on fusion categories by Ettinghoff et al. Topological quantum computation by Ring and Wang. Categorical quantum mechanics by Samson Abramsky and Bob Koike. Tensor categories by Ettinghoff et al. Thank you so much for listening.
So let's thank Khyathi for a wonderful talk.
Thank you.
And are there any questions? So if not, then I will stop the recording.